We are entering the last week of this course, and in the last week, we discussed about the two-way slab analysis and design, and we covered first module. What are the difference between one-way slab and two-way slab? And we also discussed the code coefficient method. And in the second part of the module, we discussed in detail about direct design method, which is also called as DDM, direct design method. In this module, we are going to discuss another important method, which is a more generic method, which is called as equivalent frame method. So, expected learning outcomes after the student goes through the video, the student should be able to discuss the basics of equivalent frame method, how the equivalent frame is derived, and what is an equivalent column, what is its significance, and one example also will be solved for the design of two-way slab using equivalent frame method. Right. So let's get into the equivalent frame method. You can see a plan view of a slab system here. So what you observe here, these highlighted regions are basically the frames that we are going to talk about in the east, west, and north, south direction, right? But if you look at the plan view, and you find that you have circular column here, and you have square column here, and you have a beam that is only on this span, right? On this, if you look at the leftmost, you have both the transverse beams are there, and then you also have some edge beam, right? And if you look at here, in this location, you have a column capital, drop panel, and a column. So you are having different structural systems in different spans. Even if you take this one particular frame in the east-west direction, and if you look at the sectional elevation of this system, what you see here is a slab that is running along the all the four spans, but the support system is keep changing. For example, this is a, let's say, square column, and this is the edge beam, and then if you look at the next support, you have a circular column, and then you have a column capital, and then the next support, if you look at it, you have a circular column capital, and this is your drop panel, right? And if you go to the next support, you have a transverse beam that is running perpendicular to the plane that what we are seeing. In addition to that, this is a proper beam that we have. So for the same frame that we are considering, your supports are changing quite a bit. One span, you don't have any beam, and the rightmost end span, you have a beam supported slab, and then in between, you have a flat slab system only with column capital. Another one support, you have column capital plus drop. So like this, you have varying boundary conditions. Such kind of systems you cannot design using code coefficient method or direct design method. So you need to create your frame, equivalent frame, and do structural analysis using moment distribution method, which is a very popular method. Okay. So in this approach, what we actually do here is just like in direct design method, the slab is divided into series of two-dimensional frames in each direction, that is north, south, and east, west direction. And we are going to calculate the positive and negative moments using elastic frame analysis. So to do frame analysis, I need to know the stiffness parameters for the frame, right? How to arrive at the stiffness parameters when the boundary conditions are changing, that is what we are going to discuss. Okay, and this method is very satisfactory for symmetrical frames as well as for those with unusual dimensions or loadings. Okay, so if you remember, we had different limitations of direct design method, right? Successive span lengths cannot be differing more than one third, and then live load to dead load ratio cannot exceed more than 3, like that, and column offsets should be within certain limit. All these limitations were there in direct design method. These limitations can be overcome using equivalent frame method. Only thing is the column lines you have to be careful. The column offset here also it should not be too far. I would say that is one thing. If your column offsets are too high, then again equivalent frame method, it will not give you proper thing because you cannot really assume, or you have to have a different widths for different spans. So like that we have to do. Okay, that is one of the things. If your structural system is very irregular, then I think going for finite element analysis is better. But for somewhat regular structures with not too much column offset, but if it has different boundary conditions like the one that we are seeing in this slide, then definitely we can use equivalent frame method. Okay. So once you calculate your moments, that is basically what we are doing is, if you remember in direct design method, there are three steps. One is calculation of your total static moment. Second one is calculations of longitudinal distribution of moment. And the third step is transverse distribution of moments that you got from your longitudinal distribution analysis. Now, in the same way, in this equivalent frame method, what we are really trying to get is longitudinal distribution of moments. Once you get that, in the transverse direction, it is distributed in the same way like what we did in direct design method. Absolutely, there is no change. Right? Load transfer system. Now, let us look at in an equivalent frame, what are the different load transfer system that you have. Okay. So, as we have seen in the previous slide, you are having the main element that is transferring the load is slab beam member in the main direction of bending. Then you have supports in the form of a columns or walls. Now, this is the third one that we have to be careful. The frame also is going to have, if you take frame along in this direction, you are also going to have transverse beam which are running perpendicular direction, so or orthogonal direction, transverse to the frame, that is along the L2. Why this is called as torsional members? Because when the slab beam is bending, it is going to create twisting in the perpendicular direction, in the transverse direction. That is why we call these as torsional members. Okay. Now, if you look at this one particular span from the left and right side of the column, what you have here is a column above and a column below, and this is your width. So, what is this width of this element? It is going to be from here to here. When you look at it, it is going to be L2, right? The width of the frame itself, right? In fact, okay, just because this, if you're going here, this is going to be L2. Okay, L1 is the direction of the spanning, each span. So you see here, you have a beam that is running along the column line. Then you have another beam that is running perpendicular in the transverse direction. So that is going to contribute by twisting. So that is why this is called as torsional member, where the stiffness has to be considered in the form of KT, which is your torsion stiffness. Right. So these are the elements that are being part of the load transfer system in an equivalent frame. You have column above and below, and you have a slab beam element. Why we call it as a slab beam element is, in flat slab, you are not going to have a beam. When you have a beam supported slab, you'll have both slab and beam, that will be the main element that is going to transfer the load to the connecting elements. So that is why we call them as slab beam elements. Okay? In a flat slab, beam will not be there. Right? And the transverse member, which are going to contribute in torsion. Now let us see. Our whole idea is somehow to come up with an equivalent frame. Okay, the properties for beams, slab beams, column above and below, and then you have to include this transverse beam that is going to contribute in torsion. So usually you can have slab system differing in a in a multi-story building. Different floors can also have a different slab panel systems. but it is typically you try to keep the same floor system for every floors or the same slab system for every. Then what we do is if you do analysis for one particular substitute frame, then it is this design is going to be same because the column positions are not going to change. If it is going to change, of course, we have to do that particular flooring differently. Because once the column positions are fixed, then the typical floor arrangements are going to be nearly same. So what we are going to consider is only one typical floor of a multi-story frame like this, and it is we can consider this far ends to be fixed, which is a reasonably a good assumption, right? And like this, we create one particular substitute frame of a typical floor, and we are going to consider that the far ends of the columns to be fixed. Then what we do is we convert the column above and below into an equivalent column, right? And so we are going to convert this into now a single story frame because so that it is easy for me to analyze. So how do we convert that? Now the column above and below can be represented as one element or one equivalent column. And then in addition to that, you can also lump this beam that is running in the transverse direction as a torsional beam. And usually what we do is we combine this transverse beam and the column above and below into one thing that is called as equivalent column for simplicity. Okay, because when you do frame analysis, I need to know the stiffness of the horizontal member, which is a slab beam, and the vertical member. In the vertical member, now what we are doing is for a typical one substitute frame, we are converting the column above and below into one single column. In addition to that, I'm also going to have a transverse beam if at all it is there, and you're going to add them to the column and above, below and above into an equivalent column. So equivalent column has stiffness of column above and below. In addition to the torsional stiffness of the transverse beam. So that is what an equivalent column is. Okay, now let us see what is a slab beam element. What are the things that we need to take into account in a slab beam element? If you recall your structural analysis, we know that for a prismatic member, that means when the beam cross section doesn't change along the length of the beam, for a fixed support like this, to create a rotation theta, right, I need to apply a moment which is equal to, let's say for generic boundary condition, it is moment applied should be equal to k into theta. Now what should be k for a, when the far end is fixed, k will be 4 by L, right? So to create unit rotation when the far end is fixed at the near end, when I'm creating a unit rotation, I need to apply a moment of 4 by L. So you know that. And then we also carry over because now that I'm rotating this near end support, some moment will get carried to the far end also. That carryover factor, if you remember, it is going to be 0.5. Okay. And also the fixed end moment in a uniformly loaded beam is WL square by 12. Okay. And if you remember your displacement method of analysis, how do we do? First, we lock the two joints because I'm blocking these two joints from preventing from rotation. When load is applied, I'm going to develop some negative moments at the two supports, which is equal to WL square by 12. Then what we do? Slowly we unlock and lock the joints in a successive manner until the joints has achieved its final positions of rotations. That's what we do in moment distribution method. But you don't explicitly do this unlocking and locking of the joint, but what you do is you try to balance the moments in the joint. Okay, that is in a way it is rotating the joint to the desired level that what we want. Okay, so anyway, so for a prismatic system, you are going to have a k factor of 4 and a carryover factor of 0.5 and a fixed end moment of WL square by 12. Now, in this case, as we have seen in the first slide, your members are not going to be prismatic because you're going to have different supports at different points, right? So you're going to have a stiffer member at the column joints region, and Stiffer means usually when we talk about flexure, it is actually EI by L. L is anyway fixed, but EI is going to keep changing. So the EI can keep changing. For example, at the slab column joint region, EI is going to be greater. And slabs with the drop panels and column capitals will be stiffer than the column itself because now you put a capital and a drop panel. So the column stiffness is also going to change along the height of the column. So somehow, so in other words, the frame element that what we are idealizing, it's not prismatic and its cross section is changing. So the EI is changing. Somehow I have to account for that. So the equivalent frame method takes this variation in stiffness into account. For these slabs or slab beam elements, usually the K factor is going to be greater than 4 because now you have stiffer elements along the length of the beam and along the height of the column. And carryover factor will be greater than 0.5 and fixed end moment is going to be greater than WL square by 12. So whatever the typical values that we assume for prismatic members, in this case, now we don't have prismatic case and the members are getting stiffened at the column supports as well as along the height of the column. So all these coefficients are going to be higher than the usual values. So how did we get these values depending upon the boundary conditions? Professor Hardy Cross was the first one. He used column analogy method and developed these values depending upon what kind of support condition that is. So already American Concrete Institute code as well as Canadian codes and European codes. They have these tables that are ready-made available depending upon the standard boundary conditions. So using these tables, depending upon what is the length of your drop panel, what is the length of your column capital, already tables have been derived and these values can be taken from those tables. Okay, so K, carryover factor and fixed end moment for different boundary conditions. Okay, so that's what we are also going to use in this part of the module. Now, we talked about the EI is going to change. Now, let us see how the EI is changing. Okay. So, if you look at this slab beam element, now you have this is your slab and this is your drop, right, as we have seen, and this is your capital. And if I take, that's why if you look at the variations of the moment of inertia, for example, if I look at this section AA, I'm going to have thickness of the slab only as HS, right? But if I take the section at D2, and it's going to have, let's say here, HS is equal to D1, right? So this. Now, if you look at the thickness at this section, you see that now the slab is having slab thickness. In addition to that, you also have drop panel thickness, whatever the thickness that you provide. But if the same thing, if I take the section at this point, now you see column capital is also coming depending upon where I'm taking the section, right? So it is having thickness of the slab, thickness of the drop, and part of the column capital also coming. So, and we know that moment of inertia is BH cube by 12 for a rectangular section. Now the depth is changing. So you can have a T section or you can have a varying section. So that is the reason this moment of inertia for the slab is going to keep changing along the length of the span. At this location, when you are including slab thickness, drop panel and column capital, the moment of inertia is going to be high. But when you look at it only at the drop panel location, the moment of inertia is again it's going to reduce compared to that of what you are having it at the capital region. And then if you look at only at the slab region, you're going to have a very high, a very low moment of inertia. So like this, the moment of inertia is going to change along the length of the member. Now, Young's modulus doesn't change because we pour a slab, drop, columns also in some cases together. Okay. So your moment of inertia is function of your concrete compressive strength. And usually you will have drop panels and the slab will have nearly same concrete strength and you see it will have same concrete strength, so your elastic modulus is going to be same. So that is the reason EI in flexural stiffness, E doesn't change much, only I changes. Now this column capital region or at the column region. So we can see at C, we can calculate what is the moment of inertia from what we have from the drop panel is I2 by 1 minus C2 by L2 the whole square. Now what are the C2? C2 is a column dimension in the transverse direction, and L2 is again the width of the frame in the transverse direction. Similarly, when you look at this variations of the column also, if I take this location, my column is going to have a particular, let's say if I have a square column, it is going to have a dimension of C1 by C2. So we can calculate your moment of inertia. But if I'm taking a section at this point, now you see it is also column capital is being part of the column. So your moment of inertia is going to increase as your width is increasing. And at this location, when you look at it, now it is becoming very, very rigid. Now you have entire width of the frame is going to be part of the column. So that is why we say here at this is going to reach infinity compared to that of this value, or it's going to reach a very high value, right? So in this way, I'm going to have variations of moment of inertia in slab and moment of inertia variation in column. So this is what we are saying. At section AA, if you look at it, this is I1. And section BB, when I look at it at this location, you have I2, which is this, right? And then you have at section CC, you're going to have I2 divided by 1 minus C2 by L2 the whole square. So like this, the moment of inertia is going to keep changing. Now let us look at what is the variation of column stiffness. Now you can see here, we are looking at two cases, slab system without any beams. And if you look at it, depending upon where you take the section, you're going to have I of column only. And at this location, when you take, I is going to approach infinity. So you see that there is going to be variations in column stiffness. Now the same thing, when I have a slab system with a drop panel, now you see here it's going to be infinity at this, above this drop location, and then wherever drop panel is there, that is also going to act. So it's going to have some increased stiffness, and then you have here you have column stiffness. So there is going to be again increase in your stiffness as you go along the length of the column. Now you can also have another variation, slab system with drop panel and also capital. Okay, now this capital is also there. So you see here again the moment of inertia variation is going to follow this same. Anything that is above, it is going to be infinite, because now the entire slab is going to be part of the column. So the joint region is going to be very, very stiff. That is the message that what we are trying to tell. Similarly, when you have a slab system with beams, okay, beam supported two-way slab system, which we solved example in the last part of the module in direct design method, again you are going to have variations in stiffness levels. So in nutshell, what is that we are saying here is, you have variations in stiffness of the slab beam element, you have the variations in the stiffness of the column. And for a typical moment distribution method, the standard values of K is equal to 4, carryover factor is equal to 0.5, and fixed end moment is equal to WL square by 12. Now, because we are dealing with the stiffer elements along the length and the stiffness is varying, these coefficients have to be tweaked depending upon what dimensions that we have. Now there is another important thing we said, we convert this slab system into an equivalent single story. In that single story frame, there is something called equivalent column we talked about. Let us see what is equivalent. So the equivalent column consists of columns above and below the slab and the one that is attached to torsional on both sides of the column. So the stiffness of the column can be taken as KEC. Now let us see how this KEC is derived. Now you see, you have a column above and below. Both of them are in parallel. So you can add this column of above and below as one column stiffness. In addition to that, this is what we said, when this kind of frame is joined, this is a rigid joint, right? So when this rigid joint, let's say before deformation, it is like this, right? And then when you apply the loading, then your frame, the joint is going to rotate like this. Okay, so this is your theta, right? So this is what the joint rotation in a rigid joint. Both the elements that are connected in the joint rotate by the same magnitude, right? Now consider this beam and column frame. if I know the stiffness of both frames, right, that is basically stiffness of this beam and stiffness of this column, we can calculate this joint rotation theta, right? Okay. So in this case, now in our two-way slab system, what is that we have? We are not only having this column above and below and beam like this, we also have this beam, transverse beam, that is going to, when this joint is rotating, okay, when this joint is rotating in bending, there is a member that is connected along the joint in the transverse direction that is going to undergo same magnitude of theta in twisting. That element is going to twist because it has to satisfy deformation compatibility. So that is what we are calling this as twist as rotation theta b in the joint. Okay. Now, what is happening is close to the column region. Okay. So, if you assume this my body as my column, so anything that I move away from this support column, my hand is going to be more flexible, right? So, in the same way, the transverse beam is going to have more rotations as we move away from the joint region. So, theta A and theta C is going to be larger than theta B because they are more flexible. So somehow we need to calculate this average twist of this transverse beams because the twist is not the same, right? So that is what we are saying. So the rotation theta B is at the column beam joint. Now the rotations theta A and theta C are at the end of the torsional beam are greater than this theta B, and because it is more flexible. Okay. As a result, when I calculate the stiffness of the torsional beam, I have to calculate this average rotations along the edge of the slab. Okay, that is line ABC. And that is going to be greater than what I am going to get at the joint rotation. Okay, somehow I have to account for this flexibility of the torsional beam as we move along the transverse direction. Okay, now let us see how do we do that. Okay, so why is it we are talking about equivalent column? Because somehow I have to include this partial stiffness of the transverse beam into the calculation, right? So the concept of an equivalent column is basically introduced to account for increased flexibility of the connection of the slab beam member to its support. Now the slab beam is connected to the column. Yes, at the joint, right? But for most of its width, it is through torsional member that is running the transverse direction. Because slab beam is connected only in the column. Column is having finite width where the joint is forming. But for most of the other parts, I am having this torsional member in the transverse direction. That is what it is connected to the slab beam element. So we have to account for this increased flexibility. Now you see here, two columns are connected top and bottom. They are in parallel. So you sum the stiffnesses of this column. Now this column and the transverse beam, they are connected in series. Okay. So that is why when two springs are connected in series, right? So how do you get your equivalent stiffnesses? 1 by K equivalent is 1 by summation of column stiffness above and below plus 1 by stiffness of your transverse beam. Okay. So if you substitute that and then simplify this, the equivalent stiffness of the column can be expressed as stiffnesses of torsion stiffness of the transverse beam and the flexural stiffnesses of the column member. Okay. And you know what is stiffness of the column member? 4EI by L. In this case, L is going to be height of the column. Similarly, we need to find expression for how to calculate the torsion stiffness of this transverse beam. So now let us see how to do it. And you know that C is something similar to moment of inertia in torsion. Okay, so this is your 9 EC by EC is elastic modulus C by L into 1 minus C2 by L2 the whole cube, which is similar to your, we write flexural stiffnesses Ke by I by L. Okay, depending upon the boundary condition, the K value will change. Similarly, I am going to have EC by some fraction of your L. Okay, so let us see now what are these things. EC is your elastic modulus of concrete. Once your concrete compressive strength is fixed, EC is fixed. And C is a torsional property of the section that is similar to your I. This is similar to your moment of inertia that we do it in flexure. Okay, this is the torsional stiffness parameter. And what is C2? C2 is the width of the equivalent rectangular column, capital or a bracket, measured transverse to the direction in which the moments are being determined. So C2 is an equivalent rectangular column. Okay. So now let's calculate how to do calculation of CE and all that we will see in the example. But basic concept is this: column and above, they are connected in parallel. Transverse beam is connected to this equivalent summation of these two column stiffnesses in series. So you calculate your overall equivalent stiffnesses, KT into summation of KC divided by KT plus summation of your KC. Okay, again, so in the torsion stiffness, we said, why is it? So we have again said equivalent column consists of columns above and below the slab and attached torsional edge beams on both sides of the column. Now, what is the equivalent column stiffness? If I apply some moment in the joint, I have to divide it by average rotation of the edge beam. Okay, so an inverse of stiffness 1 by k, we know that it is flexibility. It is equal to the average rotation of the joint between the edge beams. Okay, so in other words, what is the average rotation of your equivalent column? It is the rotation of the column itself plus the average beam twisting that is happening. Okay, this you see, this is an average twist, like what we said. At the end, it is going to twist more, so you take an average twist. So this is the basic concept of determining the equivalent stiffness of your column. So now let us see. For we talked about KT parameter, right? EC into C divided by some L factor, right? Now what is C? The C is your torsional constant, similar to your moment of inertia for any cross section. And now for edge beams, either it can be an L section or it can be an I section, depending upon what kind of shape of the beam that you have, the edge beam, right? And typically it will be L shaped, right? So if you see here, the L shaped beam that it is shown here, it can be discretized. What we have to do is we have to discretize them into two rectangles like this, okay? But I can either discretize this way or this way. Two ways I can discretize this L section, right? But when you do this discretization, usually you need to get the maximum value for this C. So you discretize this L section in such a way that, and you sum them up all the things. So what is X and Y here? X is always a small dimension and Y is always the larger dimension, right? So you have two elements, two rectangles here. So one is X2, Y2, another one is X1, Y1. So when you do that, always make sure that when you take the bigger of this X elements should have longer length, right? So we will show that through example. So when you discretize them, if you see the shorter dimension of the bigger element, you have to take it to be, let's say you have x1 and x2. Let's say x1 is 100 and x2 is 50. Then you take x1, the whichever is a larger, that element should have longer length, that is longer y. Okay, if you do like that, your C value will become maximum. Or in other words, you have to discretize in such a way that the C value is going to be maximum. Okay. So where what is X and Y? X is the shorter overall dimensions of the rectangular part of the cross section, and Y is the longer overall dimension of the rectangular part of the cross section. Now the cross section has to be divided into separate rectangular parts and carrying out the summation in such a way to give largest value of C as shown in the figure. So in this case, if your x1 is greater than x2 because x1 is having longer y1, then this configuration will give higher C. You will have a more C value. Okay. So in that way, we have to discretize. Now let's see. So these are some of the uh, detailing aspects. Okay. And as we have said, once our intention of equivalent frame method is to find the longitudinal distribution. Once the longitudinal distribution is found, then we do transverse distribution by appropriating the moment to column strip and middle strip, like what we have done in the direct design method. That process is exactly same here also in the equivalent trade method. Okay, so the code gives you some guidelines how much is the minimum percentage of steel that I need to put at the top location and bottom locations. So that is given as a fraction of your LN, the span, the clear span over which it is acting. So these different dimensions are given in the code. We need to follow this detailing guidelines. Okay, right. So now let us see how this stiffness factor. So we have seen why that stiffness factor, carryover factor, and fixed end moment factor is going to be higher than the usual values of 4, 0.5, and WL square by 12, 1 by 12, right? So you can see here, you can have different conditions like this. This is a case that we are looking at for a flat plate, right, without any drop pattern, right? So in this case, if you see here, and CN1 and CF1 is, this is the near end, okay, near end, and this is the far end, okay, and one always indicates the direction where we are calculating the moments, and two is the transverse direction. So for that is the reason column will have C1 and C2. C1 is the direction in which that we are calculating, so that is what this is, and similarly CN2 and CF2 are the transverse direction, and L1 is the span, main span, for which we are doing the analysis, and L2 is your transverse direction or the width of your frame. Okay, and now in this case you can have loading, okay, in such a way that not the entire span may be loaded. The loading can start from center line at a distance of AL1, and it can stop also at a distance of BL1. Now A can be 0 also, and similarly BL1 can be going till the end also. So these values that are given, the fixed and moment coefficients, they have been derived for a typical standard value of B minus A equal to 0.2. Then you keep your A, and then you can find the tables, and how these values are derived using column analogy method and the equation. For example, if you look at it, Cn1 by L1, if I'm having, because span will be fixed based on the architectural record. Column dimensions also will be fixed based on the load that particular tributary area is going to the column, right? So let's say, for example, Cn1 by L1 for the dimension that what I've chosen is working out to be 0.1. Now, depending upon the perpendicular direction, now let's say again L1 and L2 are nearly same, right? So Cn1 by L1. So if your spans are same in both directions, then we end up providing a square column. Then Cn2 by L2 is also going to be same. So if it is 0.1, this is also going to be 0.1. These two values are fixed. Now, you see here, when these two values are fixed for this kind of a flat plate system, I am having stiffness factor of 4.18, and carryover factor has slightly increased from 0.5 to 0.51, and uniform fixed end moment coefficient, okay, and is, see, let's say if it is uniformly loaded, that means everywhere you are having same load, there is no B and A. So in this case your fixed end moment coefficient is 0.0847. But if you have only intermittent loading, not the entire span, then depending upon what is your A and B value that you have fixed, then these fixed and moment coefficients can be found out. If it is uniformly distributed, this is the value that we are going to use. So now we got your K value. Now we got your C carryover factor. We also got your fixed end moment coefficient. So I have now all the values that is required for carrying out moment distribution. So like that we have to do for all the spans. Okay. So once your stiffness parameters and loading parameters are fixed, then it is a routine process of carrying out moment distribution only. Okay. So these tables have been taken from Pillai and Main and reinforced concrete design. In fact, these were recreated from the values that are given in your ACA standard 318. So the next variation is you can also have flat slab system. So you have a drop pan. Same way. Only thing is, first case we looked at flat plate. Now we are looking at flat slab because it is having a drop pan. Now again, the drop panel dimensions I have to standardize. Okay, here, if you see here, drop panel dimensions have been kept as L1 by 3, and this direction it is L2 by 3. And because I for to arrive using column analogy method to derive these stiffness factors, I need to fix some standard dimensions. People have fixed standard dimensions as a fraction of your span lengths, then the tables have been arrived at and it is readily available. That is what we are going to use. Okay. And how these coefficients are derived is using column analogy method. That description is outside the scope of the work. You can look at structural analysis course videos where they will tell you how to use column analogy for non-prismatic members to calculate the stiffness parameters. So that is what we are looking at. If you look at this, you see here, this is the slab stiffness, EC and IS. And at this location, now you have a drop panel. The moment of inertia is going to increase like this. At this location, we have a, though it is going to increase quite a bit. So this is the value that we are going to take. It is going to increase, right? So this stepped variation of a moment of inertia that it has been assumed here. And then these coefficients have been derived. For example, again, if you look at Cn1 by L1 as 0.1, Cn2 by L2 as 0.1, your stiffness parameters now you see it has increased to 6.04. Similarly, carryover factor has increased to 0.6 in from 0.5. And fixed and moment coefficients also increased, assuming that entire span is loaded, right? Instead of uh, in this case, AL1 is going to be 0, A is going to be 0, and B is going to be equal to 1. Okay. So if that is the case, the entire span is loaded, then you are having this coefficients. Okay. Again, for this loading and this configuration of flat slab, now we, depending upon what is the column dimensions, what is the span that you have, you can use these tables to find this K factor, carryover factor, and fixed and moment coefficient, right? Now what are the stiffness and carryover factor for columns? Okay. Now in a frame, I'm having a column as well as a slab beam element. Slab beam element we discussed in the previous part of the module. Now, what are the stiffness and carryover factor for columns? So you can see it is EI by H typically, and K value is going to change. Now again, why is it changing? Because the moment of inertia is here, it is there. Here you can have again flat plate, and here it is flat slab, and here I have flat slab with capped column capped, right? So this is how we get. So your moment of inertia is again going to vary along the length of the column. So again using column analogy method, depending upon what is your TA by TB ratio. Now what is TA and TB? Some terminology we have. In a flat plate, it will be same. So it is basically for the top portion of the column, you take from the center line of the slab to the bottom edge of the slab. That is TA. Similarly, at the bottom support, top surface of the slab to the center line of the slab. So usually the slab dimensions are same. Your TA and TB is going to be same for a flat plate. Okay. But in case of a flat slab, you see, we are measuring TA as from the center line of the slab to the bottommost point of the drop panel. So TA is going to be higher than what you are going to have for flat plate. Similarly, what is TB? TB, there is no change. So TB actually center line of the slab to the top surface of the slab. So TB in flat plate and flat slab is going to be same, right? So similarly, if you see here, what is TA for a flat slab with capital? I come from center line and I go all the way to the edge of the column capital. So TA is going to be higher than what you're going to have for a flat slab with only drop, right? So like that for different boundary conditions, already people have done the analysis using column analogy method. And you can also, you see one more factor, height to clear height, HC. That ratio, based on that, people have derived this coefficient. For example, let's say TA by TB equal to 0.2 and H by HC is equal to 1.05. You get K factor of 4.31 and carryover factor of 0.56. So see, like that I need to do for both top end as well as at the bottom end. Okay. Now, for values of other end, KBA and CBA, instead of TA by T ratio, we have to use TB by T you have to inverse, right? Now the definitions are going to slightly change because column will have two ends, right? So I have to find out the stiffness parameters for both ends like this.